All right, so today we'll be talking about sound waves, but also imaging, of which in this particular case, we're talking about medical imaging. So this is a very important topic in physics. And in today's topic, we'll be solving a lot of questions about sound waves, but also imaging and their clinical applications. So the reason or the whole reason behind learning this particular topic is to understand its medical application, its medical importance, how it's applied in hospitals and in different healthcare setup. So let's start with question one, which is saying, um, a canyon echo, I don't know if it's a canyon echo is heard 4 seconds after shouting. The canyon echo is heard 4 seconds after shouting. If the speed of the sound in air is 340 meters per second, of which this is the general speed, or this is a constant value for the speed of sound in air. So those who attended the class, they'll understand to say this is the constant value. It never changes. This is the speed of sound in air. So if the speed of sound in air is 340 meters per second, estimate the distance the canyon explain the distance to the canyon wall. Explain the distance to the canyon wall. All right, so they want us to calculate distance in this particular case. And one thing that we need to pay attention to is that they are talking about an echo. What they're talking about is an echo. So the sound that we are hearing is an echo, which means sound has been produced. It goes in a certain direction, or sound waves travel in a certain direction. They hit a surface and they bounce back towards the origin of the listener. So the echo is being heard 4 seconds after shouting. The echo is being heard 4 seconds after shouting. This is very important. And as I have said, the sound waves are being reflected off a distant surface and they are returning back to the listener. So in this particular case, the canyon wall is the one that is reflecting, or what that is acting as a reflecting surface, because it is the one that is actually reflecting the sound waves in this particular case. So what are we supposed to remember? Since we're describing an echo in this particular case, one thing that we're supposed to keep in mind that is that the distance that the sound waves are going to travel is the distance from the person who is shouting to the canyon wall, but also from the canyon wall after bouncing back to where the listener is, which means the distance that we've been given is being traveled 2 times. So we have 2D as the distance that is being traveled from the shouting person to the canyon wall, then back after reflecting from the canyon wall to the listener again. So this is a round trip in short. So we know to say in order for us to calculate distance, when we've been given or when we want to calculate velocity in short, we say velocity is equal to distance over time, like that. Of which, if I want to calculate distance in this particular case, what am I going to say? I'll say this over 1, of which this is going to become distance being equal to velocity multiplied by time, like this. But since in this particular case, the distance that we are covering is a round trip, which means it's 2 times the distance that is initially between the person that is shouting and the canyon wall. The distance here should be doubled, which means this equation is going to change from d is equal to velocity multiplied by time to being 2 multiplied by distance being equal to velocity multiplied by time, like this. So since I want to calculate the distance only, I'll divide both sides by 2, even that side by 2. This will cancel out. That means my distance will be equal to velocity multiplied by time divided by 2. This is how we calculate distance when it comes to an echo. So D here is the distance, we have velocity, we have time. I mean the total echo time. This is the total echo time. That's one thing that you're supposed to keep in mind, not the time that it's taking the waves or the sound waves to travel from the shouting person or from the source to the canyon wall. It's the echo time, which means from the time you shout to the time you hear the echo. So I can just say this is echo time for clarity, like that. Okay, so now that we have this equation, they've asked us to estimate the distance to the canyon wall, and we've come up with an equation to calculate distance to the canyon wall. So I'll just say my distance to the canyon wall would be the velocity Since we've already been given the velocity to say it's 350, multiplied by the echo time, which they've given us to be 4 seconds, divided by 2. This is going to give me what? So 340 multiplied by 4, this is giving me 1,360, and this divided by 2. So that means the distance from the person to the canyon wall is equal to 680 meters. As simple as that. So this is the formula that we use when we're trying to calculate the distance that has been traveled by, or distance being traveled by an echo if we've been given a echo time. As simple as that. Very important. Question B is saying if the echo is heard again, which means you are now hearing the echo for the second time. Remember, we heard the echo the first time after 4 seconds. Now they are saying if the echo is heard again after 8 seconds, what does that tell you about the echo's origin? What does that tell you about the echo's origin? So here there is nothing that we need to calculate. We just need to explain. After understanding the science of sound waves and an echo, the way an echo behaves, we are now supposed to show our understanding by answering question B, because they're asking us to say, you've already heard your first echo after 4 seconds. Now, after 8 seconds, what happens? You hear another echo again. What does that tell you about the echo's origin? So do you have any idea about that one? This was part A. Can now talk about part B. Hello? What does that tell you about part B? All right. So if we only had one echo, we are going to conclude to say the source of there's only one source of this echo, because an echo can only be heard if there is a wall or an object where sound waves are bouncing back from, bouncing back to the listener. Now, in this particular case, we are hearing two echoes. And if two echoes are being heard at two different times, what does that mean? That means there should be two sources of echoes. What do we mean two sources of echoes? That means there should be another canyon wall which is at a different distance. Remember, we've calculated to say this canyon wall where the first echo was heard from after 4 seconds was at 60 or at 680 meters. If you hear another echo after 8 seconds, what does that mean? It just means that there is another source of that echo, which is a different canyon wall, and that canyon wall should be where? Should be further from where the first canyon wall is, which means sound waves first bounce back off the first canyon wall, then others proceed to the second canyon wall and also bounce back. But since it has at a longer distance from the listener, they are going to take a little bit of much time in order for you to hear them. So there are two walls here. There is the first canyon wall where you hear the first echo from, and there is another canyon wall again where you're going to hear your second echo from. So this one is taking 8 seconds, whilst the first one is taking 4 seconds like that. So this is the only possible explanation that we can give here, because we are hearing two different echoes at two different times. So that means there should be multiple reflections, multiple sources of the echo, as simple as that. So the sound that you hear or the echo that you hear in the second time or after 8 seconds is because of the second uh, reflection from the second canyon wall. As simple as that, of which this second canyon wall should be at a distance that is further from the first canyon wall. As simple as that. That is the only explanation that we can give here. Is there anyone with a question? All right, so if there's no question, let's proceed to question two. And question two is saying an ultrasonic sensor emits a sound wave at 40 kilohertz. An ultrasonic sensor emits a sound wave at 40 kilohertz. It detects an object zero point 0.5 meters away by measuring the time delay of the reflected wave. It detects an object zero point 0.5 meters away by measuring the time delay of the reflected wave. Okay, so when they are talking about the reflected wave, it's the same principle that we used when we're talking about an echo, huh? Because even an echo, it's a reflected sound wave. Now, what are they telling us here? They're telling us measuring the time delay of the reflected wave, which means there is a wave that has been reflected also in this particular manner. So there are two questions again. Question A is saying, calculate the time taken for the wave to reach the object and return. Calculate the time taken for the wave to reach the object and the return. So here basically we're using the same principle that I was using in part one. They want us to calculate the time, the total time that is taking for the wave to reach the object and the return, which means it's the total time for the echo, or it's the echo time in this particular case. It's the echo time like that, the total time for the round trip, which means from the time the wave is produced for it to travel to an object and for it to bounce back again and be detected. And in general here, this is how the ultrasonic imaging works. Huh? Have you ever been to a hospital where they subjected you to ultrasonic imaging? Because here they're just detecting the echo, which that's the principle that the or ultrasonic imaging uses. That's why they've talked about it, an ultrasonic sensor in this particular case. So what are we going to do? We're going to use the principle that we mentioned. We said since it's an echo, that means the distance is twice the initial distance. So we're going to say 2 times distance is equal to velocity multiplied by time, like that. This is what we said. Which in this particular case, what do they want? They want us to calculate time, which means we'll plug in V there or divide by the V there, but also V there. So the V will cancel out. That means my time will be equal to 2 multiplied by distance divided by velocity. As simple as that, where this distance is the distance for the distance for the total round trip, the distance that they've given us to the object rather. This is to the object, and everything here is for the round trip. And this one is the speed of sound. The velocity that we are using here is the speed of sound. So are you able to solve this question on your own? The speed of sound, and we don't need to panic with the speed of sound because we've already looked at it and you said it's a constant value. Even here, you might get confused where we're getting the distance of sound, but they've told us to say it's emitting a sound wave, which means we're supposed to use everything that is in reference with a sound wave, especially velocity, because it's a constant value. It doesn't change. So this is how we're going to do this. So the time will be equal to 2 multiplied by the distance that we've been given here, which is 0 0.5, divided by the speed of sound. So the speed of sound is equal to what? It's equal to 340 meters per second. That's what they've told us in question one. 340 meters per second. So I'll divide everything here by 340 meters per second. So I'll say this will be equal to 1 meter divided by 340 meters per second. That means the total time that it takes for the wave to reach the object and return back to be detected or to be detected by the sensor will be equal to, let me just say 1 divided by 340. This is giving me 0.0002 0.294. 0.00294 seconds. So this is the time that it's taken for the wave to reach the object, but also return back and they get detected. As simple as that. Then question B is saying if the sensor's pulse duration, if the sensor's pulse duration is 0.01 seconds, can it accurately measure this distance? Explain why or why not. If the sensor's pulse duration is 0.01 seconds, can it accurately measure this distance? Explain why or not. Okay, so this is also a conceptual question. This is part B. This was part A here. This is also a conceptual question. They're telling us to say if the sensor's pulse duration is 0.01 seconds, can it accurately measure this distance? Explain why or why not. So, what do you understand by this question? What do they mean by pulse duration? What do they mean by pulse duration? Because they're saying if the sensor's pulse duration is 0.01 seconds, can it accurately measure this distance? Explain why or why not. What do they mean when they say pulse duration? Hello? What do they mean? Okay, so when it comes to these sensors in this or in ultrasonic imaging, this sensor that they've given us, they've said it has a pulse duration of 0.01 seconds. Now, what does this mean? It means that for this sensor to hear an echo, for this sensor to be able to hear an echo, it must finish transmitting the sound pulse before reflection returns. I hope you understand what I'm saying. For this particular sensor that we are using, if it is having a pulse duration of 0.01 second, what must happen? The echo must return after the pulse has finished being emitted. The echo is supposed to return only when the pulse has finished being emitted. Now they're telling us to say the pulse duration is 0.01 seconds. And the time it's taken for the echo to reach the sensor is 0.00294 seconds. Do you think it will be able to measure this distance? That's now me asking you the question. If the pulse duration, in order for it to be able to detect this reflection, it should finish its pulse before this time, or it should finish before it should finish its pulse before the echo returns. Now, since this is the pulse duration and this is the time it's taking for the echo to return back, do you think it will be able to measure to accurately measure this distance? Come on, do you get what I'm explaining? I'm trying to simplify it. Like the returning echo time. This is the returning echo time. Or maybe let me explain it like this. If this is the returning echo time and the sensor has this pulse duration, for a sensor to be able to detect the distance or to accurately measure a distance, the returning echo time, I don't know, maybe I should explain it in this way now. The time that is taking the echo to return must be bigger than the pulse duration because the echo can only be measured if the pulse completes before the echo returns back. This is what I'm trying to explain. So which means the pulse or the returning echo time should be greater than the pulse duration. If you look at this one, the pulse duration is 0.01. If you look at the returning echo time, it's 0.002. 2. This time that we have here, the returning echo time, is smaller than the pulse duration of this sensor. And we are just explaining to say the returning echo time must be greater than the pulse duration for clear separation, because it must finish its pulse first before the echo returns for it to be detected by the sensor. Like that. So, what are we going to conclude here? We can conclude to say the pulse duration, which is 0.01, is greater than 0.00294 seconds. The 0.001 seconds, which is the pulse duration here, pulse duration is greater than the echo time, which means when the echo is returning, the sensor is still do what? Is still transmitting its pulse. The echo is the sensor is still transmitting its pulse when the sensor or when the echo returns. So what is our final answer? We're going to say no. No. The sensor cannot accurately measure the distance. Cannot accurately measure the distance. Why? It's because the pulse duration is greater than the returning echo time. Whereas we explained to say there must be clear separation. The sensor must complete producing its pulse before the echo returns for that clear separation in order for an accurate measurement to be taken to be measured. But in this particular case, the echo arrives back at the sensor whilst the sensor is still producing its pulse. Therefore, we're going to conclude to say the sensor cannot accurately measure the distance. That is about question 2. Is there any question? Any question? This is a very important. In case they ask you this question, please don't get lost. It's the same thing as maybe the example that I can give. Maybe when you are talking to someone, for example, and whilst you are still talking, someone else starts to reply whilst you are still shouting. Are you going to accurately get what they are saying? No, you can't, because they've started talking before they finished talking. So even here, the principle is the same. The pulse duration is the time that is taking the sensor to produce its pulse. So the pulse must first finish before the echo comes back. But here you are seeing to say whilst it's still producing its pulse, the echo has already returned, which means it cannot accurately measure. Even as human beings, if you are talking, before you finish talking, someone starts talking, it starts answering or shouting back, you cannot clearly get what they are saying. You need to first finish what you're saying, then let them respond. Then you can get clearly what is happening. As simple as that. Let's move on to question 3. Question 3 is saying a police car emitting a siren at a frequency of 800 Hz approaches a stationary observer at 30 meters per second. A police car emitting a siren at a frequency of 800 Hz approaches a stationary observer at 30 meters per second. So in this particular case, there's an observer who is a human being, of course, and there's a police car that is emitting a siren. A siren is, of course, producing sound waves. And they're trying to say it is producing those sound waves at a frequency of 800 Hz, and it is approaching the person, which means it's moving towards the observer. It's not stationary. It's moving towards the observer, getting closer to the observer at a speed of 30 meters per second. That's the statement that we've been given. Now, the first question they're asking in part A is, what is the observed frequency when the car is approaching? What is the observed frequency when the car is approaching. All right, so this car is approaching this observer at a speed of 30 meters per second. Then there is an emitting frequency. The frequency at which the siren is emitting its waves, which is 800 hertz, like that. Now they want us to calculate the observed frequency. The observed frequency by the observer when the car is approaching. When the car is approaching. So when sound waves, or maybe let me say when you are observing sound waves from a moving object, it might be moving towards you or it's moving away from you. That phenomena, we call it the Doppler effect. Have you ever heard about the Doppler effect? Have you ever heard about the Doppler effect? Okay. Right. So just as I am explaining, the Doppler effect is just the apparent change. Can I say it's a change because I've explained it? So it's a phenomena. The source of the wave is moving. It might be moving maybe towards you, because sometimes you might find that the car is approaching you, and at some point it's going to cross where you're standing as the observer, then it will start moving away from you. So that phenomena, we call it the Doppler effect, because there is a change in frequency, and this change in frequency that we are going to experience is caused by the motion of the source and the observer. The motion of the source of the wave, but also the observer. Very important. So when, let's say, when someone, or when the source of the wave is moving towards you, you're going to find that the waves are going to become compressed, such that the wavelength is going to decrease, but the frequency of that wave is going to get very, very high. So in order for us to calculate everything that they're talking about here, we're going to use the Doppler principle, or the Doppler equation itself. What does the Doppler formula state? It states to say the observed frequency is equal to the emitting frequency, open bracket, a velocity here, over velocity there, plus or minus Vs, like this. This is the Doppler equation that we use when the motion, or rather the principle that you are discussing, is the Doppler effect. So you have the observed frequency here, which is the one that they're asking about here. Then we have the emitting frequency, which is the source frequency. They've given us the source frequency to be 800 hertz. Then there's the speed here. This speed that we have is the speed of a sound wave in air. And we know to say the speed of sound wave in air is 340 meters per second, like this, divided by speed of sound in air again, plus or minus speed of the source. This Vs is V of source, which is the speed of the source. And what is the source here? It's the ambulance, or the police car, not the ambulance. Sorry, I'm relating the ambulance siren and the police siren, which is this one that we've been given here, which is 30 meters per second, like this. Now, if the car is approaching the observer, this equation is going to become observed frequency will be equal to source frequency V, which is speed of sound in air, over V minus Vs. If you are being approached, this is it. If you are being approached by the source. If the source is going away from you, there's going to be a change in this equation, which means the observed frequency will be the source frequency V over V plus V over the source, like this. What's the opposite of approaching? What's the opposite of approaching? Anyway, I don't know. Just say if the source is moving away from the observer. This is how these equations actually work. So in part A, they are saying what is the observed frequency when the car is approaching, which means we're just basically using the equation that is at the top. So which means I'll just say my observed frequency will be equal to the source frequency, which is 800, open bracket, 340, which is the speed of sound in air, over 340, which is the speed of sound in air, minus the speed of the approaching source, which is 30, like this. So I'm going to have 800, 340 divided by 310. 340 divided by 310, like this. Okay. So this is going to become, if I divide 340 divided by 10, 310, what do I get? 340 divided by 310?
1.097.
1.097, like this.
Yes.
Okay, so you multiply 1.097 multiplied by 800. What answer do we get as the observed frequency?
877.42.
877.42 hertz. So this is the observed frequency when the source, which is the police car, is approaching the observer. As simple as that. Then part B is saying what is the observed frequency after the car passes the observer moving away. So it's now moving away, but the speed is still the same. It's moving away, but the speed is still the same. So what are we going to say? We're just going to do the opposite of what we did in part one. So what are we going to say? We're going to say the observed frequency, which is in B now. The observed frequency will be the frequency source, speed of light over speed of light plus speed of the source, like that. Since now it's moving away, there's going to be a plus here. So this is going to give us 800 hertz, open brackets, 340 over 340 plus 30. Okay, this is going to give us 800, 340 over 370. Okay, like that. So if we divide 340 by 370, what do we get? 340 divided by yes,
0.9.
0.9.
0.919.
919, like this. Okay, so that means finally our observed frequency will be equal to what?
735.14.
735.14 hertz. As simple as that. Is there any question here?
No.
All right, then let's move on to the next one, which is question 4. Question 4 is saying in medical ultrasound imaging, a pulse of sound with frequency 5 megahertz, this is megahertz, million hertz, 5 megahertz is sent into the body. The sound wave reflects off a tissue boundary 3 centimeters deep. The sound wave reflects off a tissue boundary 3 centimeters deep. Part A, how long does it take for the echo to return? How long does it take for the echo to return? Okay, so we've been looking at such a question since question 1. Are you able to solve this one? We're now calculating time. We're calculating the time that is taking the echo to return. And remember, we said the distance is equal to velocity over time. But since it's an echo, that means it's 2 times the initial distance. So say 2d is equal to velocity over time. What are we going to do? We're going to make time the subject to the formula by dividing both sides by velocity, which means our equation will be time will be equal to 2d divided by velocity, like this. We're trying to calculate the time that is taking the echo to return. Whilst distance here is the depth. They've given us the depth to be 3 centimeters deep. That we want this depth in meters. So I'll divide this one by 100 and I'm going to get 0.03 meters, like this. So this is the distance that I'm going to plug here. And the speed here, remember, what is the speed of sound in a tissue? This is not in air now. Remember, in air, it's 340 meters per second. What about in a tissue? The speed of sound in a tissue? It's 1,540 meters per second. This is in a tissue. These are known values. So if you are lucky, they'll give them to you in your exam. But these are known values that you can actually just master. There's nothing very difficult about them. So we're going to say our time will be equal to 2 multiplied by 0.03 divided by the speed, which is 1,540. This is going to give me 2 multiplied by 0.03. I'm getting 0.06 divided by 1,540. That means the time it's taking will be equal to, it's a very small time, 0.00003896. Okay, let me just put exponent, shift exponent. This is giving me 3.9 times 10 to the power minus 5 seconds. So the time is 3.9 times 10 to the power minus 9 seconds. This is the time that is taken the wave to reflect off the tissue boundary, that is 3 centimeters deep. This is part A. Part B is saying if the speed of sound in tissue is approximately, oh, they've already given us this one. If the speed of sound in tissue is 1540 meters per second, estimate the depth of the tissue boundary based on the measured echo time. X, what are they saying? Estimate the depth of the tissue boundary based on the measured echo time. So how are we going to answer question B? It's reversing the previous calculation. They're just asking us the previous calculation. We're now trying to calculate the distance. And remember, we said distance is equal to velocity multiplied by time divided by 2, like this. This is the formula that we're using. Now, we've already calculated the time here. So what are we going to say? We're going to say velocity, which is 1540, multiplied by time, which is 3.9 times 10 to the power minus 5, like this, divided by 2. This is going to give us 0.06006 divided by 2. And this is going to give us a distance, which is 0.03 meters, which is the same as what? As 3 centimeters. So they're just asking us to